Hello! So of course this is the second part to our video covering eigenvalues and eigenvectors for 2x2 matrices. This video focusing more about why we care about these things and why they are important. So now that we've calculated eigenvalues and eigenvectors for 2x2 matrices, we might be wondering why they're useful. Well, some of that utility just comes from what we like to do with the eigenvalues and eigenvectors once we've found them. And one of those uses is to help us find invariant lines of a matrix transformation, which shouldn't entirely come as a surprise considering the method for finding eigenvectors does have a lot of similarities with how we set up how to find invariant lines and points, as we have previously shown. But there are a few differences that we do need to point out. Firstly, acknowledging that eigenvectors are solutions to the matrix equation, the matrix transformation times by the eigenvector must equal lambda lots of that eigenvector, where lambda is a scalar value, being the eigenvalue, lots of that eigenvector. That means that applying the matrix transformation to a particular eigenvector is the same as just multiplying that eigenvector by that eigenvalue, which is therefore actually quite easy and quick to do. So if we look at things graphically and we've got a point, let's say it's the coordinates 3, 1, and we're dealing with a matrix transformation that has an eigenvector of 3, 1, and let's also say it's got an eigenvalue of 2 for that particular eigenvector, then if we transform this point 3, 1 using our matrix transformation, then because it's an eigenvector, transforming is the same as just multiplying it by the eigenvalue. So therefore 3, 1 will just become 6, 2. Now, looking at this graphically might be enough for some of you to already see a bit of what's going on, but let me spell it out fully just so that everybody's on board here. We need to be aware of the fact that when we're applying matrix transformations to a point, we're not really applying it to coordinates per se, we're applying it to the position vector of that point. And as a reminder, a position vector is always a vector that takes us from the origin to that particular point. So for instance, the position vector 3, 1 takes us from 0, 0 to the coordinates 3, 1. But then also we had that other point 6, 2, and the position vector of that would be 6, 2, therefore also being a vector taking us from 0, 0 to that point. And therefore, because our new point was just a multiple of the position vector of the old point, of course, if we take the multiple of a vector, we end up with a parallel vector. But not just any old parallel vector. Because both these are position vectors, they're both starting at 0, 0, so they share a common point, meaning they are therefore collinear, or in other words, lying on the same line as each other. And that's guaranteed to happen anytime you're starting with a position vector and just multiplying it by another number. You're going to be left with a line going through the origin. But it's worth noting that our point did change position when it was transformed, but it just changed positions to a place somewhere else on that same line, which of course you'll hopefully realize is just what an invariant line is. And therefore this is going to be a relationship that's true for any eigenvector, because all eigenvectors can be multiplied by their respective eigenvalue to be equivalent to just applying that matrix transformation to that eigenvector. And therefore, in general, we can say that eigenvectors provide the direction vectors of any invariant lines, but only invariant lines that go through the origin. So actually, that's why you did need to know another method for finding invariant points and invariant lines, because this method for finding them only works for finding invariant lines that go through the origin, whereas the other method we've shown before helps you find any invariant lines at all. But now we've established this fact, let's take a look at an example. Let's say we've got the matrix transformation 3, 2, 1, 4, and we want to find the invariant lines, but only the ones that pass through the origin, which is lucky because that means we're allowed to just use this eigenvectors method. Of course, if we're going to use this method, we first need to find what the eigenvalues and eigenvectors are, but luckily we've already used this matrix in previous examples, so we already happen to know that the eigenvalues of this particular matrix are 2 and 5, and that the eigenvectors that go with those eigenvalues were 2, minus 1, and 1, 1 respectively. These are though just the direction vectors of the lines, not the equations. And admittedly, the question didn't say whether it wanted vector equations or Cartesian equations. Obviously, read the question to check what format they want the answer in normally, but I'm going to write them as Cartesian equations. But I therefore got to convert these direction vectors into something I can use to write as Cartesian equations. Of course, the direction vector is telling you how you can travel along the line. So for instance, looking at the direction vector of 1, 1, that's telling you every time you go 1 to the right, you must go 1 up to travel along the line. Therefore, the change in y over change in x to work out the gradient would be 1 divided by 1, which of course would be 1. Therefore, meaning our invariant line would be y equals x. And then for the other eigenvector, we had the eigenvector 2 minus 1, which means every time we go 2 to the right, we go 1 down, and therefore change in y over change in x would be minus 1 divided by 2, meaning we get the other invariant line of y equals minus a half x. And both those lines are ones that are going through the origin, that's why we don't need to find what the plus c is. But therefore, we're done. Those aren't necessarily all the invariant lines of the matrix transformation, but we only need to find the ones that went through the origin, and these are the only invariant lines for this matrix that go through the origin. Cool, so that shows one use of eigenvalues and eigenvectors, and also gives a partial explanation as to what eigenvectors are themselves. They're linked to the direction invariant lines are going in. But that still doesn't explain the significance of the eigenvalues themselves. So let's have a go at explaining that now. And in honor of the fact we're now going to be looking at the really cool stuff, I thought, you know what, let's turn on the face cam. To know what's really going on, it all goes back to how we define two-dimensional space though, with coordinates and vectors. By now, the idea that we have an x-axis and a y-axis is well ingrained, as it's due to these axes that we split coordinates up into separate numbers for what's happening horizontally and also what's happening vertically. However, there is a more nuanced way you can look at it when you're viewing it in terms of vectors. Instead of looking at a column vector as just always being first number x, second number as y, you could instead view coordinates as just multiples of how far we have to travel in certain directions with vectors. The x value is indicating how much of the vector 1, 0 we're using, or in other words, the I vector, and the y value is indicating how much of the vector 0, 1 we're using, alternatively known as the vector j. Through a linear combination of I and j like this, we can reach any point within real two-dimensional space, which means that I and j together form what is officially known as a basis. A set of vectors is said to form a basis when every point in a vector space can be reached using a combination of the vectors in your basis. Because we're so used to this x and y or I and j structure, almost everything we do with coordinate geometry ends up being built around the system, both in terms of how we write things, as we already mentioned, but also how we calculate things. For instance, we quickly get used to the fact that we can apply transformations independently to the x and y directions without it affecting the other direction. An x direction stretch only affects the x coordinates, and also similarly, a y direction stretch only affects the y values, with no collateral damage. But it actually does not have to be this way. Of course, there is some logic to specifically choosing the axes to be in the directions we've chosen, because by having them at right angles, it means you can travel to points in an efficient way, without having to double back on yourself. But somebody would be perfectly entitled to come along and say that they want to define the axes in a different way and have them at different angles, and maybe even randomly call them the P and the Q axes. Of course, it would make things weird, because distorting things in that way would mean the coordinate grid would not be divided up into squares anymore. But we could still use this new system to be able to reference any point in 2D space using values of P and Q. For instance, this point could be 4, 1 under this new system, but that point would be of course in a different place to where 4, 1 would usually be for x and y Cartesian coordinates. Just in the same way that the point 4, 1 in polar coordinates is also not talking about the same place, because we're using a different way to measure where things are. You could still convert back to your more familiar and comforting x and y system that you're used to if you know the direction vectors of these new axes, because the values of p and q are just giving you the combinations of these vectors in our new basis that are needed to find our position vector. But here's the cool part. If you have a matrix transformation that has two eigenvectors, if you decide to use the eigenvectors as the axes for your new coordinate system, this matrix can now be seen for what it really is. Some stretches, but not in the x direction or y direction, instead a stretch in the direction of the two eigenvectors. The scale factor of these two stretches? Just the eigenvalues for those respective eigenvectors. And crucially, these two stretches happen independently of each other without having an effect on the other eigenvector direction. Yeah, Take a moment to think how cool that is. It means that a large number of transformations are just all secretly stretches, just not ones that are happening horizontally and vertically. There are exceptions to that, which is of course any transformation that does not have two eigenvectors. We looked at an example of one of those matrices before when looking at repeated eigenvalues, but also name checking a more famous example of this, a shear transformation, if you've ever heard of those. Words can only mean so much though, so let's take a look at this idea in action. Not because you ever have to do things in this way, but because it just helps us understand what transformations are doing. So in our example, we're going to be using the transformation 3214 to transform the point 10 minus 11. Of course, this is the transformation we've already used several times in these eigenvalues examples so far. But I'll tell you what, to make sure that what we're about to do that's new makes sense, I'm going to first start by applying this transformation to this point in the usual way that we do it for matrix transformations, just so that we can get an answer that we can then compare to what we do with the new approach, so that we can then check that what we're doing actually makes sense. So I'm going to take our matrix transformation and I'm going to just multiply it by the point. So we're going to do 3214 times by 10 minus 11. And if we were to do that, we get 3 times by 10, which is 30, plus 2 times by minus 11, which is minus 22. And then also we're going to do 1 times by 10, plus 4 times by minus 11, which is minus 44, which will get us the position vector 8 minus 34. Okay, so that is what we should get when we do this new approach. So in the new approach, we need to know the eigenvalues and eigenvectors. We already did that though for this matrix transformation earlier, and we did point out that we have the eigenvalues 2 and also 5, and the eigenvector that went with the eigenvalue of 2 was 2 minus 1, and the eigenvector that went with 5 was 1, 1. We could start by then trying to use these vectors as the basis to split up our point 10 minus 11, basically to find the p and q coordinates of our x and y coordinates 10 and 11. So therefore what we're saying there is we're saying there's a linear combination of our two vectors, 2 minus 1 and 1, 1, that can come together to make the coordinates 10 minus 11. To find out what those are, you could rewrite these as simultaneous equations. So of course we've got 2p plus q is equal to 10, and we've got minus p plus q is equal to minus 11. You could solve those simultaneous equations manually, or you could even use matrices. So of course pq is just going to end up equaling the inverse matrix for those coefficients, so 2, 1, minus 1, 1 inverse times by 10 minus 11. And if you work that out, it will come to 7 and minus 4. Cool. So we now know what the p and q values are under our new almost coordinate system that we've defined as. But how can we use that? Well, what it means we're saying is we're saying the point 10, 11 can now be written as, or should I say 10 minus 11, should be written as 7 lots of 2 minus 1 plus minus 4 lots of 1, 1. Okay, so that's what we've got so far. Now we want to apply the transformation to our point 10 minus 11, but doing it to its new format that we've written it in. The reason we want to do that though is because it turns out this transformation is secretly just doing a stretch scale factor 2 in the direction 2 minus 1. So what that means we're going to do is it means when we're doing 3, 2, 1, 4 times by 10 minus 11, it's the same as just taking what we had before in the 2 minus 1 direction, which was 7 lots of 2 minus 1, but now stretching its scale factor 2, so multiplying that by 2. And then we are also doing a stretch scale factor 5 in the direction 1, 1. So before we had minus 4 lots of 1, 1, but now we're going to be stretching that scale factor 5, so we're going to be doing 5 times by minus 4 lots of 1, 1. So therefore that means we've got 14 lots of 2 minus 1, and we've got minus 20 lots of 1, 1. Let's work out and see what that comes to. we're going to get 28 and minus 14 minus, or let's add it as a negative number even, so add negative 20, negative 20. That will get you as a final answer 8 and also minus 34, which is of course the exact same answer we had before. So now you can see how these matrices are working with the eigenvalues and the eigenvectors. The eigenvalues are just the stretch scale factors, and the eigenvectors are just the directions those stretches are happening in, which is so cool and makes us have a whole new understanding on how most transformations are working. You know what's really crazy though? Rotations. Rotations also fit into this system, but the weird thing is rotations are secretly most of the time just stretches with a complex numbered scale factor in a complex vector direction. Wow, that's really amazing to think, and that's why I love this stuff, because it just blows my mind, certainly the first time I ever came across it, and it just means we can look at things properly now that we know what eigenvalues and eigenvectors actually do. Okay, I think we've talked enough in this video for today. Hopefully I'll see you in a future video, because there's actually more things we can use eigenvalues and eigenvectors for that is also going to be really useful. So stay tuned for those future videos as well. See you later. Goodbye.